solution stoichiometry. We talked about this little section here yesterday when we were doing our molarity calculations. Volume times molarity does equal your moles of solute. So we will definitely be using that for solution stoichiometry. So I'm going to do 2 problems, and that's really all we're going to do on that, because at this point we have beat stoichiometry like a dead horse. We've done regular stoichiometry, we've done gas stoichiometry, and now we're going to do solution stoichiometry, which quite frankly is the one you use the most often, because usually we're mixing solutions together. And so let's get to it. So in this example, I have copper and silver nitrate as a single replacement reaction, and it wants to know how many grams of silver can I form with excess. That means we get to do a happy dance. It's not a limiting reactant. With this, whoops, sorry. There we go. With that volume of that molarity. So we're going to start with our molarity. And so we have moles of silver nitrate over liters of solution. So if we multiply by volume, we can get rid of our volume, and then we're back to moles. So I'm going to put 0.208 liters. Of course, that's over 1. So now I've gotten rid of liters, and I'm in moles of silver nitrate. So I'm already in moles, so what can I go straight into? No, mole ratio, because every stoichiometry problem needs a mole ratio. Okay? So from the balanced equation, I have 2 moles of silver nitrate, which will yield 2 moles of silver. Now I can use the molar mass of silver, 107.87 grams of silver over 1 mole of silver. And I put that into my trusty handy-dandy calculator. And I need 3 sig figs. So I'm going to say 2.24 grams of silver is how much I could form. Okay? So really and truly, the second part of that is the same as what we've been doing with stoichiometry. It's this little part right here, volume times molarity, to get to moles. Okay? So you have to take your molarity. I know your molarity is moles per liter, but if you just use that number without multiplying by volume, you will not have moles. You have molarity. You're isolating how many moles you have in the particular amount of solution you're using. Okay? Yes, ma'am.
So the 0.100 molarity, you transfer that about 0.100 moles of silver nitrate?
No, I didn't. I have 0.1 moles per liter of silver nitrate. Remember, molarity is defined as moles over liter, right? That's why you have to multiply by volume, so you can cancel it out, so then you can have moles. Does that make sense? Okay, so let's do the next example. This one, same problem, so still the single replacement. This time I want to know what volume of that I can form. So I don't want to start with that, okay? I'm going to start with my reactant. So same thing, 5.20 moles over liter of silver nitrate. I want to get rid of liters, so I'm going to multiply by the volume. Cancel, cancel. Now I have moles of silver nitrate, so now I can use my mole ratio. Silver nitrate is 1. I'm not silver nitrate, copper 2 nitrate, sorry. Told you I was sleepy. Now, I don't need mass here because it's asking how much volume of the 3.5 molar. Okay, so I'm going to use that to cancel out my moles of copper nitrate. I'm going to say 3.5 moles of copper nitrate is 1 liter. So cancel, cancel. So I plug all that into my calculator and I get 0.033 liters or 33 milliliters. So that's how much volume of 3.5 molar I would form. Okay? Any questions on that? It's all about your units. You can put your molarity wherever you need it to be, as long as you're getting moles to cancel or getting liters to cancel. So you manipulate it based on that. Did you have a question?
I got it.
Oh, I just answered it? How about that? Okay, so that's going to take us to the last thing we're going to do in the notes, which is colligative properties, which is one of my favorite words. I just think it sounds cool, colligative.
That sounds scary.
Colligative. Nah, it's not scary. Okay, so colligative properties of solutions are, there are some characteristics of solutions that do not depend on the size or the identity, but only upon the concentration. So we care how much we have. Okay, the physical properties of the solutions are different than the original solvents, and the colligative properties depend upon the number of ionized particles. The more particles, the greater the effect. Okay, so if we're going to have something that's going to affect the colligative property of something, the more particles we have, the greater the effect. So, okay, doesn't matter what it is, it matters how much of it there is. Okay, so there are three types of colligative properties that we're going to look at. Okay, this sentence got left out of your notes. I need to put some major stickies on the notes for next year. Part of the problem is I copied the wrong notes for you guys, and I apologize for that. You do not have to add the sentence if you get the gist of it, and the gist of it is the way that colligative properties are effective is because the non-volatile solute that we add results in a change to the solution because it interferes with the solution's ability to do phase changes. So it either slows it down or speeds it up. So it changes that. Okay, like I said, you don't have to write it, but if you want to, you can also paraphrase. Okay. Okay, so let's talk about how we determine the number of particles, because that's going to be important for the calculations in colligative properties. If it's an ionic compound, remember when we dissolve ionic compounds in water, they break apart. So this is going to have 1 plus 1 is 2 particles. When sodium sulfate breaks apart, 2 plus 1 is 3 particles. 3 plus 1 is 4 particles for ammonium phosphate. Okay, that's all we're doing is adding up how many particles. So we do include the coefficients. The polyatomics, however, do not break apart. They stay as a particle. Okay, so they don't break apart into the sulfur and oxygen for sulfate or the phosphorus and oxygen because they're covalently bonded. Okay, so your ionic compounds will break apart into their ions. If you have a covalent, which means molecular, or an organic molecule, they do not break apart. They are one particle only. Remember yesterday when we talked about electrolytes and non-ionic, and polar covalent, we said they don't dissociate. So like sugar, which is sucrose, table sugar, like you put in your coffee, is C12H22O11. Looks like it should have a lot of particles, doesn't it? But it's only one, because it does not break apart. The water surrounds it, but that part, it stays all together, bounded up. So it would actually have a much smaller effect on a colligative property than, say, the aluminum chloride, which would have 4 particles. Okay? This next little section is just practicing that if you want to go through. I have not been going through that today because we need to get to the calculations. Okay? This says it got left out of your notes, but it didn't. It's number 3. Okay? When it's on the bottom of that page where it talks about the types of colligative properties, it's just out of order because we're not going to do any calculations with lowering of the vapor pressure. But what you do need to understand is that if you add a non-volatile solute, it lowers the vapor pressure. And essentially, vapor pressure, the higher the vapor pressure, the more likely it is to become a gas. The vapor pressure is the measure of the volatility of a liquid to become a gas. So like the gasoline that you put in your car has a very high vapor pressure, very readily becomes a gas. Okay? But if I were to add a non-volatile solute, it lowers that, and it wouldn't become a gas as regular. Okay? But we're not going to do any calculations with that. You just got to understand that. The other thing it affects is osmotic pressure, like for osmosis and stuff. It affects that as well. But we will do boiling point and freezing point, okay? So there's just kind of showing you a pictorial of the changes when you have pure water versus one with a solute added to it. So it lowers some stuff, but it actually raises the boiling point. So the first one, now we're going back to number 1, is boiling point elevation, meaning it raises the boiling point. So if I add that non-volatile solute, it raises the boiling point. Okay? So example is adding salt to water. How many of you, when somebody cooks or you cook or whatever, spaghetti, you add salt to the water? How much do you add? Just a little sprinkle? You're wasting your time. It's not doing anything. Okay? You're not adding enough for it to do anything. Why do you do that? Why did whoever showed you to do that, why did they tell you to do it? Huh? It does flavor the pasta, but again, if you're only putting a little dash, it's not doing anything. Okay? Does anybody say it makes the water boil faster? That's what a lot of kids will tell me. It makes the water boil faster. It actually does not make the water boil faster. It actually makes the water boil slower because it's raising the boiling point, so it takes longer to get there. However, when you put your pasta in there, it's cooking at a higher temperature. Not a great higher temperature because most of you aren't putting that much salt. When I put salt in my pasta water, I open up the cap and dump a bunch in there. It looks like I'm putting way too much. My pasta is never too salty, but it cooks good because I'm putting more particles. Because remember, the more particles or the higher the concentration, the greater effect. Okay? So it's a boiling point elevation. Okay? So it gets higher. So the formula that we're going to use for this is delta T. What does delta mean? Change in temperature is equal to KB times little m times little I. I will explain what those things are in a moment. Okay? I'm going to get through the two types first. Okay? So that's boiling point elevation. Okay? The next one is freezing point depression. Okay? Whenever they think it's getting close to freezing outside, what do they put on the road? Salt. I mean, a while ago we put salt in water to make it boil higher. Now we're going to put salt in water to make it freeze lower. Has their opposite. So freezing point, when I add a non-volatile, lowers the freezing point. And its formula is this. Delta T equals KF times M times I. They look very familiar to each other, don't they? So now I'm going to show you what those things mean. Okay, so KB is called your molal boiling point constant. So if KB is your molal boiling point constant, what do you think KF is? The molal freezing point constant. So really and truly, you only have to memorize one formula there, right, Josh?
Yeah.
Because if it's boiling, you use KB. If it's freezing, you use KF. M is, what is little m? Molality. Molality of solution. And I is something called the Van't Hoff factor, which is a fancy way of saying number of particles. So a while ago we figured out the number of particles, we throw that in the equation. Okay? You will be given any KBs or KFs you need. You do not have to memorize those. That would be just mean. Okay? So let's work a couple of problems. Well, let me give you all a second to write that down. I go too fast. I'm sorry. Everybody got it? Okie dokie. So, on the last page of your notes, you have a little chart at the top. It's got your some boiling points, some freezing points, some KB values and KF values for some different substances. You might need those today for your worksheet, so make sure you have your notes handy because they're recorded there for you. Okay. So the very first example in your notes, the KB value is a typo that they gave you next to the problem, so cross that out. It's actually 0.512 from the chart. Okay, so we have 75 grams of sodium sulfate is added to 800 grams of water, and it wants to know what is the boiling point of this solution. So sodium sulfate looks like this. So how many particles would it have? 3. So it's going to have 3 particles because we're going to be using delta T is equal to KB times molality times I. So we have the KB because it's a constant. Now we have the I, so we have to figure out the molality of the solution. So in order to do that, we're going to say 75 grams of sodium sulfate. And what do I need to get it to? Moles. So I'm going to divide by the molar mass. Now I'm in moles, so I'm going to divide by the kilograms of solvent, which is 0.8. So I do all that, and I get a molality of 0.66 little m. So now I can plug it into this equation. So delta T is 0.512 degrees C over m, little m. Earlier today, or actually all day, they've been asking me, do I have to put this in Kelvin? And the answer is only if your molal constant has Kelvin. This has Celsius, so keep it in Celsius. Okay? So we're not going to convert to Kelvin. We pretty much just do that for gas laws. Some things need Kelvin, but we pretty much try to stick to just the gas laws. 0.66 molal and 3 particles. So when I calculate that, I get delta T is 1.01. Now, is that the boiling point of the solution? No, it's just the change. What is the boiling point of water all by its lonesome? So since this is a boiling point elevation, I'm going to add my 1.01 to it. So my new boiling point would be 101.01. Now, if someone wrote 101, it'd be okay because we're doing sig figs, but I want you to see that you added that to it. So the biggest mistake kids make is they stop here and say, oh, I did my calculation. That's not the new boiling point. The new boiling point is that added to your temperature. Okay? So if I added that much sodium sulfate to that much water, I would expect my boiling point to go up by 1.01 degrees. Okay? So let's do a freezing point, and then I have a challenge problem for you if you're interested. It's worth, the winner gets 5 Starbursts of your flavor choosing. Okay. So I don't have, for some reason on my PowerPoint, I do not have the second problem, which is what is the freezing point of 35 grams of magnesium sulfate. So I'm just going to do it on a blank screen. You guys have it. I just don't have it in my PowerPoint. Okay? So this time we're dealing with acetic acid, so we're not going to look at water. Gives us the KF value. So we have 35 grams of magnesium bromide. I know that I'm going to need a molality, so let's go ahead and get that. 184.11 is its molar mass. And then my volume, or my moles of salt, not moles of solvent, kilograms of solvent is 0.4. I can hear you chewing. Let's not do that. Miss Parker has issues with eating noises. It's a condition. Oh, wait, that's see, you distracted me. I'm giving you the answer already. That's not that. See, The molality is 0.475. Well, that would have really given us some strange numbers. Okay, so that's our molality. So now we're ready to do delta T equal to Kf times M times I. Kf from the chart is 3.90 degrees Celsius over molality times 0.475. How many particles does magnesium bromide break into? 3. So now I get delta T is, now it's 5.56. But is that my new freezing point? No, it is not. So this is a freezing point depression, meaning it lowers it. So Kai is right. I'm going to subtract it. So I go to my chart and I see that the freezing point of acetic acid is 16.6 degrees Celsius. I'm going to subtract 5.56 degrees Celsius, and I'm going to get 11.04 degrees. This is my new freezing point. Okie dokie. All right, so that's the end of the lesson and the end of the notes. So stop.